Folks who were not in the morning session, we covered part 1 this morning. And right now we're going to cover part 2 and part 3. So facilities for class design and these larger language features, initialization, movement semantics, lambda expressions. Hopefully this should be fairly close. Ooh. Okay. So part 2, features supporting better class design. So we'll look at default override final keywords, delegating constructors, inheriting constructors, initialization of stuff in a class, and conversion operators. So one of the ancient problems in C++ is how to keep it from letting you copy something. So you have a class, maybe it's going to be a built-in special case, but generally speaking, how do you just disallow copying? If a client tries to make a copy of an object, it doesn't work one way or another. So the two sort of legacy approaches. Number one, declare those copy operations private, right? When we talk about copy operations, we're talking about copy or copy assignment operator. Those are the two. They always go together, or usually. Declare them private. That works. It's a little problematic. Another way is have a handy-dandy base class you can inherit from privately, because an RHC is not a non-copyable. This is not an is-a relationship. So you use a private inheritance, which is an is implemented in terms of relationship, really, and make sure that this class is not copyable. So maybe this one does that or something else. An example is boost non-copyable, something available for this purpose. And this is not because it's self-documenting, right? This is a little bit more obscure. Anyway, I'm not going to go into all the pluses and minuses of these, but they're not perfect solutions. Fortunately, C++11 does give you the perfect solution. If you're not going to allow something to be used, you just say equals delete. Notice the clever recycling of an existing keyword. So that's a good thing. Question, what does it mean? This means that the class does not contain those member functions. And the compiler will not generate one for you. That was both the question and the answer. Note that the names are still public, right? So there's a difference between whether something is available versus visible, accessible versus actually implemented. So it's good to keep track of that stuff. So it's not a scope error to try to make a copy. You're not going to get some kind of a diagnostic saying, I don't know what you mean, or unrecognized function. You'll get a very clear diagnostic saying, sorry, that's been deleted, or something to that effect. You can also explicitly specify using the default, meaning the one the compiler would generate if you didn't declare it. And that's really useful because just omitting it means that the compiler generates it for you. You don't have another constructor that you've provided. Right? But how would you get the default constructor generated for you if you already have another constructor? You'd have to write it. So you'd have to actually implement it. Maybe you just put a pair of braces, no big deal. It's a little bit more self-documenting to say, I just want to let the compiler generate it for me. And the only way to express that, if you have another constructor, is to say equals default. Question? Well, they don't, because those are generated functions, and they don't inherit. Question? OK, the question was, how does the equals specifiers affect derived classes? I don't believe they have any effect on derived classes. I mean, they'll affect derived classes in the sense that when you create a derived class and it tries to call the base and it's not there, you'll get an error. But in terms of how it changes the behavior, it's going to be a compile time error. You'll get errors if something tries to use a copy constructor.
Well, for example, if you derived a class, would that class be able to create an assignment operator, even if the base class says that there isn't one?
Yes, absolutely. Because when assignment operators are the odd duck in the set of generated functions, because all the other generated functions, the constructors, whether it's default or copy constructor, and the destructor, all have to have access to the base class counterpart. If you don't, it just never works. Assignment operator is different. You can write an assignment operator for a class and the base class doesn't have to have one. So for the assignment operator, a derived class could have one. Why you would want that to happen in this case is beyond me. It doesn't sound like good design. But technically, it's legal. Right? So I'd like to go back and re-answer the original question. What effect does making these delete have on the derived class? It basically means you can't let the compiler generate those for the derived because it won't be able to. It won't be able to call the base class versions. Okay? Yes? Why were some of the solutions on the previous slide not optimum? See me after class and I'll go through it. Okay, it's well documented. It's old stuff. So I want to try to fit the new stuff in. Okay. So here is an old C++ class hierarchy. So we got a base class and we got F and G, which are declared virtual. G is also const. We have a non-virtual function H. Then we have a derived class. In old C++, there's a lot of potential confusion here, or just outright errors. So if someone is just looking at this code, let's say this is an addition module, so I'm not really seeing that. If you just looked at this line, how do you know if F is virtual or not here? You don't. You have to know if it's virtual or not in the base. So that's confusing. Is this G meant to override base's G? Let's say you even knew that base has a G, but you're not really thinking about the declaration. So was this meant to override this or not?
Well, it won't.
It won't, but you don't know what was in the mind of the person who wrote that line. It's not clear what the intention was. It's confusing and ambiguous in some sense. Not to the compiler. It's ambiguous to somebody trying to read the code. What does this do? Does this override base's H? No. Because to override, it has to be a virtual function. That's the definition of the word override. So what's...
On the other hand, if you have a variable of type derived, then it will use the H in the derived class. If you have a variable of type base, it will use the H in the base class. But if
There's
you
all
have
sorts
a
of...
situation where you think you're overriding,
Okay.
but you're really not.
So the question is about the behavior of having these two H's. I don't want to consider that because it's horrible design, it's a mistake, don't do it, end of story. This is a mistake.
Sure.
There's very limited number of use cases where redefining or hiding a name is a good idea. It's the majority of the time this happens in a code base, it's a mistake. Okay? So again, you can't look at this and know if the person who wrote this intended this to be an override or not. Because the person who wrote it might have expected it to have been virtual. Or maybe they didn't even understand that it has to be virtual to be overridden. So those are all the mistakes. Now let's see how all those issues are solved. So in new C++, there's a couple of new keywords, final and override. You can declare a member function final. That means it becomes a compile error to try to override it or redefine it. You get a compiler error here. Good. No one should have ever done this. Now, if your intention is to override, you just say so. I want this to be an override. For this to be an override, the base class counterpart must exist and be virtual. And if it doesn't compile. Same thing here. So this is correct. Presumably, we are trying to actually override this virtual F, so that's the right way to do it. This will generate a compile error, and you'll go either, oh, I didn't mean to put the const there, or, oh, I meant to put a const here. One of those two, probably, is going to be what you say after oh. And you fix it. And then this just doesn't compile. Now, the punchline here, final and override have not been existing keywords. The Standards Committee hates to create new keywords because every new keyword that's created and injected in essentially breaks code. Somebody could have had a variable called final. That's not hard to imagine. Or override. These are contextual keywords. They only have the behavior they have when you use them exactly where you're seeing them. And if you use them as the name of a variable, fine. You can still have an int final inside of h. The question is, you have to remember that there's an equals default equals delete. I would suggest when you're writing a class, you use each of them to their fullest capacity. And then there's no more having to remember anything.
I just thought maybe they do not be consistent, so it has, it's kind of a label for the function. So
All four of these, the equals default, the equals delete, the final, the override, they're meant to clarify intention and let the compiler enforce the intention and avoid silent weeks of debugging. Yeah. Maybe not so silent. Weeks of debugging. All right. So I love the fact they're contextual keywords. That's like an awesome invention. Question?
can you specify final derived class?
You mean like that? The question was, can you do that? Okay? Yes, a class can be declared final. That's how you do it. It is also a contextual keyword, and it doesn't break any legacy code. Yeah.
I remember the containers in the old C library, C++ library, like Vector, for example, do not have virtual
Correct.
constructors.
Right?
So those have to be final classes, right? If you, because I've done this, and
They don't have to be. Okay, the question is, what about stuff like STL containers that are not polymorphic? They don't have a virtual destructor. So the reason they don't have a virtual destructor is there's a performance cost for that. And if you really want to employ a vector, most people do it through containment. Is it legal to inherit from a vector? Sure, but you better not try to use a mixture of vectors and super vectors polymorphically, because then you'll be in deep you-know-what. So the language is permissive, right? It lets you do that if you really want to, but it's not designed to support polymorphic use of vector as a base class. That's all. Okay? So final classes. In old C++, constructors could not leverage other constructors of the same class. If you learn Java and you see how Java constructors just call each other, you go, why can't I do that in C++? Well, now you can. In C++ 11, a constructor can call another constructor. So let's say we're trying to model flux capacitors. So here's 4 different constructors for flux capacitor. And the one that's really the workhorse, well, actually, in this case, there isn't any. I'm sorry, this is the example of old C++. So everyone duplicates effort, which means you now have real potential for error here. If you leave out some of these steps in any one of these constructors, you'll be in trouble. And in fact, there's a logic error here. I'll get you started, see if anybody can spot the logic error. And it's not going to be diagnosed by the compiler, most likely. So the default constructor sets capacity and ID. ID is driven off of a static counter, basically, that you use to keep a rolling index number for your flux capacitors. Because when they're going back and forth in time, you can get quite a few of them all. You definitely need a multi-threading environment to really make use of that. The one that takes a double will instantiate, will initialize everything. One that takes a complex, etc. Anything about the bug here? Not flux capacitor, but there is something uninitialized.
Where do you initialize
Capacity, that's the bug. This constructor does not initialize capacity. It's got garbage. Okay, so that's the old scenario. In 11, in new C++, this is the workhorse. The one that takes the complex actually does all the work. So it validates, it sets the ID to the next available number, it initializes the capacity. So now, it's a lot harder to forget to set the capacity. As soon as these other constructors are coded to call this one, or either directly or indirectly, that issue goes away. The default constructor calls the one that takes a double. The one that takes a double calls the one that takes a complex. The one that takes complex does all the work. And the copy constructor also calls the one that takes the complex. So there's less chance of failing to initialize. However, there's another subtle problem this does introduce, and there's no silver bullet for this. Now, there's a performance hit here. Anybody spot it?
Well, you have to call two functions.
That's not it. In fact, all of these are inline, and it's as if you just called one function. Yeah. Very good. You're calling validate when you don't need to in some cases. All right. Certainly when you default construct, you don't need to validate, right? So if you're willing to pay the price of calling validate a little too many times, great. So now you have to make a decision what's more important.
But you can always, excuse me, if you object to the overhead, you can always write your own personal default constructor in that case instead of.
Absolutely. Okay. You can.
Yeah.
So the question is, if you don't want the overhead, you can start manually taking care. Of course, but now you have to consider what the performance issues are. So it's not a silver bullet. It's not like an instant solution to all problems. It's just one more tool in the arsenal. Yes.
Is the call to
Sorry.
another constructor first in the list of initializations?
The question is the call to another constructor. It'll pretty much follow the usual order. Okay. So this is because this is basically acts like a base initializer. The calling sequence is first. If you're default constructing as a user, the first call will be to the default constructor. The first thing that's is invoke this constructor. Then it's going to come back. It's then going to do some other initialization because that's how C++ works. And then it's going to go in here and do what's in the braces.
So you could make one call for a base class or data member before you call the other constructor.
So the question is, can you control the order of things? No, but you can specify what's going to happen for each of them. So remember, the order is very fixed. The order of initialization is absolutely fixed by the language. It always does base initializers first in the order of their declaration. Then it does member initializers in the order of their declaration. Then it does members. I mean, data members. So, or I'm sorry, then it does what's in the braces. So, and the destructors are the reverse of that. So the order of everything remains the same. So all this really adds is the ability to reuse the code in one of the other constructors than the one that's initially called. That's all. Okay. So now let's look at data. In old C++, the only types of data members that you could initialize in class, in the braces of the class definition, in here, the only things you can initialize are const, static, integral data members. Basically, and their relatives. Bools, shorts, longs, ints, unsigned, unsigned longs.
But you could do enums.
Enums were constants.
I mean, a variable that is an enum type.
An enum type, okay. But that's an integral type.
Yeah.
Okay, so it's in the family of integral types. And my theory, I don't know this for sure, but it makes sense. The reason that the language decided to allow that is so you could have an initialized variable used as an array dimension, which has to be a static const integral type. Then you can use that to show the dimension of an old-fashioned array as a data member, and that's legal. However, if you try to initialize a static variable, it's an error. If you try to initialize an ordinary data member, non-static, it's an error, right? And here's another case of forgetting to initialize capacity. So in this case, again, we have undefined value for capacity, right? All right, so this is not good. It's very limited. I guess I can't say it's not good. It's the way C++ was forever. Now it gets better. So in new C++, any data member can be default initialized in its declaration. And the compiler does what you would want it to do. So if the constructor fails to mention it, what you write down here is what takes effect. If in the constructor you actually set something, it'll ignore what you said down here, and it'll do what you told it to do. It's not going to do it twice. It's not going to double initialize. We know it wouldn't do that. Okay. Oh, yeah. So now a static that's not const can be initialized. The ID starts at 0. Why not just say it right here? Wasn't it a pain to have to declare the darn thing outside the class? And then you have to remember, do I put it in the header or in the CPP file? Yeah, it's the CPP file. Ugh. Just stick it in there, end of problem. Even an ordinary data member can be initialized, and that's the default value if you don't do anything else. Question?
And if you had a class data member owned by this object, you could initialize it there as well.
You mean a static? When people use the term class member, some people mean static and some people mean something else. So are you talking about a static data member?
Let's say you have wheel as another class, and this is an array of wheels, and you want to initialize the wheel, which is a class.
It's exactly what he's doing when he initializes capacity, complexes, and other class.
There you go.
Okay. So yes, you
So you can make this an array of complexes too and have braces and initialize that. Yes.
One example that pops into my mind, which I doubt that you can do, but it is a question, is I have a shared pointer, right? And I want to initialize it with a new, just an empty, say it's a shared pointer to a collection. And I just want to initialize it with a new collection.
Okay.
So I got a shared pointer to a list is the variable.
So the question is, you got a shared pointer to a list
Right.
as a data
I
member,
say new list type, whatever.
and you initialize it.
And I'm
Looks fine.
initializing the shared pointer.
Sounds good to me. What's the question? It's a data type. You can initialize it. Okay. Yeah.
Is there any stylistic recommendation between you initializing the variables like this and doing it, say, in a constructor where you put all the variables together and initialize them so you can see all the initialization at once?
So the question is there a stylistic preference between this way or the old C++ 98 way? That's basically what it sounds like you're saying. Because that's what the old C++ way is. You show all the initializations every time in each function, in each constructor, right? If you find that clearer, go for it. I mean, ultimately, you want to pick whatever style is going to do the best job of making it clear what you're doing. And it may very well be that using these new features make it more obscure, and you can decide as a designer you want to do it the old way. Go for it. It's a case-by-case thing you'd have to make a decision on. Yeah.
One advantage that might lend you towards, or send you towards this style, is that here we got the same default construction by supplying default initializers instead of providing lots of variants of the default, or lots of variants of the constructor.
No kidding.
Yeah, I mean, I'll try to simplify that. The comment is, the advantage is things are initialized in one place. Would that be a decent simplification of that comment?
Well, and we needed fewer constructor declarations.
Things are initialized in just one place. Sounds good. That's a good thing. Okay. In new C++, a derived class can actually inherit all the constructors from the base class. It sounds weird because, in fact, constructors aren't really inherited. So what this is, in C++ 98, it's already legal to inject into the scope of a derived class a name in the scope of the base class. And you need to do this if for some reason that name was hidden, right? If the base class has a member named X, and in the derived class you create an X that's unrelated, you've now hidden X from the base class, which is not good design, but let's say you were forced to do it, gun to your head. Now you can get back the other X, by having a using directive, and that's a bad example because you wouldn't do that. But anyway, you can inject a name from a base class into a derived class, with one exception. In old C++, it was not legal for constructors. So it was illegal to say using base : : base. And that restriction has been lifted. So it is now legal to use a base class constructor. Remember, when you use using, it's names that you are injecting into the current scope, not specific variables, not specific functions, the name. So you cannot specify, I want those first two constructors, but not the next two. Right? It has to be all or nothing. So using flux capacitor brings all the base class flux capacitor constructors into the scope of red-black flux capacitor. So if a user initializes a red-black flux capacitor the same way they initialized a regular flux capacitor, it just works. And it just uses that code from the base class. So what makes a red-black flux capacitor different? It has a color that can be either red or black. So we introduce an enum, red-black, maybe to be proper for new C++, I should have said enum class there. Either way, that works. And then maybe I'll add another constructor that just takes a color. And so that would invoke the base class constructor implicitly, and it would also set the color to whatever was provided as the constructor parameter. Right? And then it'll use the default constructor for flux capacitor, because there's an implicit call to that in here.
But in that case, it wouldn't have a default constructor that used the flux capacitor. So if I, for example...
Actually, okay, the question is, in that case, it wouldn't have a default constructor, and I'm going to stop you there because, in fact, it does. It's flux capacitor's default constructor. Becomes red-black flux capacitor's default constructor. Yeah. Okay, so this default constructor is there. So that's inherited and can be used.
But you don't have...
And it'll still initialize the color to red, because that's initialized down here in the data area. Yes?
So which is within the initialization order, does color get initialized first, or is it based on?
Okay, for which constructor? Are we talking about this one?
Default constructor.
Default constructor is the one from here.
Right.
Okay, so this constructor is going to run, and it's going to do everything it would have done here. So that's going to happen first,
And then that guy.
and then it's going to initialize color to red.
So I guess where I'm going with that is that the rule is that red-black flux capacitor has a constructor, therefore it doesn't have a default constructor. What you're saying is that by doing this, by using flux capacitor and flux capacitor, that you've done something kind of like default, only default to the previous class, the base.
All right, the question is something about whether or not there's a default constructor. I've already explained that. It's really simple. It's the one from flux capacitor. It's there. It is red-black flux capacitor's default constructor. End of story. If you didn't have this line here, there wouldn't be a default constructor. But with this line, there is. That's all. Don't make it more complicated than it is. It's complicated enough. Okay. All right. So there's this concept in C++ of user-defined conversions. People familiar with that term? So one type of user-defined conversion is a constructor that takes a single argument, right? It's an implicit conversion from the argument type to the class type, unless you say explicit. So that's always been true for C++ since forever. There's another type of user-defined conversion that's been supported in C++ forever. It's called the operator function. So in a class, you can say operator foobar, and it takes no arguments, and it has no return type because it's implicitly foobar. So double, int, whatever. And in the body of this function, you do some code that returns whatever this type is, and that's an implicit conversion from the class type rational to the class type, in this case, double. Right? So if a rational is represented by a numerator and a denominator that are longs, you can have an implicit conversion to a double, and you have to code it to do the right thing. Be careful, don't lose your fractional part, right? If you code it right, you'll get a nice double that's correct. You can make it work. The problem with this is there was no way to make this explicit. You get unexpected silent conversions from rational to double when you might not expect them. That's the pitfall in old C++. For that reason, I always recommended you never use these functions. All right, so 11 fixes that problem by allowing you to make them explicit. Just like constructors have always been explicit if you want, now this conversion operator can be explicit. Okay, so that's better. Now you can avoid silent, unexpected conversions from rational to double. Right? If you have a function that takes a double and you pass it a rational, if the conversion is active, it'll compile. But you may not expect that. But if you put explicit here, If you've got a function that takes a double and you pass it a rational, it's a compiler. So if you want that conversion, you have to code it. You have to do a cast, or you can actually do it the functional notation way, but who'd want to say dot operator double, okay? But you can do it. So I'm going to suggest, even though the language supplies this now and it's better, I still prefer doing something like Java does. Just create a two-double function. A lot of people did that in old C++. I wouldn't touch the code. Leave it alone. It's good. It's clear. Question?
So what's the motivation behind explicit conversion operators?
I haven't read the papers to know what their motivation was, other than without it, it was absolutely hideous. So with it, it's less hideous than it used to be. Okay? The question is, what's the motivation for this? It's an improvement. It's just not ideal. I would recommend just don't use it. But I bet there's a bunch of other experts here who would come up with use cases that it would make a lot of sense. I just don't see those, because I don't do a lot of production code. All right, so that's class design features. Moving on, we're going to cover initialization, languages, move semantics. All right, initialization. Okay. There's a lot of complexity here, and I know there's going to be a lot of questions that comes up in people's minds. What I'd like to do is ask that maybe we limit it to one or two quick questions on each of the topics, and then I'm going to kind of crack the whip and we're going to move on, because I'd love to get through to the end of stuff today. Okay, so limited initialization. In C and C++, you can initialize an array of built-in types. If you have a struct, you can initialize their members. All right? So this is basically both C and C++, except that in C you have to put the word struct there or type def it or something. But that syntax is still basically valid. Unfortunately, you could never initialize an STL container using braces in old C++. It just wasn't supported. And those of you here this morning saw what you had to do instead. So that means you have to do this kind of craziness to create a variable that has the size of an array that you're going to initialize from, and then copy all that stuff into the vector. Right? Not fun. So the solution for this is the standard initializer list. Well, actually, there's several solutions, but the one that affects the STL container specifically is the ability to have a generalized syntax for providing a curly brace enclosed list of stuff that you can just pass to a constructor. And the way it works is the compiler, when it sees a pair of curly braces being used as an initializer for something, and it's not one of these legacy types, okay, because that's a special case, and we'll get to that. And there's some complexity there. Did you have a question?
Yeah, I was wondering, could you use auto when it grabbed the initializer list?
Well, there's a slide on that. Question was, doesn't auto screw you up? Yes, it does. Okay, and we'll see that in a minute. So if it's something other than one of those types of things, if it's a class type, there's an ability to provide a braced initializer list. And the mechanism is that the compiler, when it sees this, it turns it into an object called a standard initializer list. And then there's an overload of the constructor for that container that takes an initializer list. That's how it works. The equal sign becomes optional in new C++. And I believe the convention going forward is to omit it, unless you're paid by the keystroke again, etc. It looks strange, but you get used to it. Notice that this line of code is not an initialization. Does everybody see that? What is this doing to v2? It's assigning to it, right? It's been initialized already. We cannot reinitialize it. But you can use an initializer list. Well, the trick is if you looked under the covers of the vector, you'd see it not only has a constructor that takes an initializer list, it has a copy assignment operator that takes an initializer list. So what's really being initialized is the initializer list. Okay? So this thing is being initialized, and then it's being passed by reference or whatever. Actually, it's not. It's passed by moving. But it's being passed as a parameter to that copy assignment operator. And what we're initializing is not the vector here. It's nothing. We're assigning to the vector. All right? Questions on that? Here's a function, foo, that returns a vector of int by value. Perfectly fine, right? unless you know about move semantics, then if you look at this, you should get really scared. Because in old C++, that pretty much means you're instantiating an anonymous vector of ints, returning it, using it, and destroying it. Okay, yes, there's optimizations that might come into play here, but that's syntactically what that means. Let's forget about the performance aspects of this right now. It's still perfectly legal, even in old C++, to do it. All right, so here's a vector of int. We're initializing with the initializer lists, and we're using an initializer list in an STL member function operation. We're inserting these values at the end of the vector. That's fine. Here we're using an initializer list to iterate across an arranged for loop. That's fine. We can even return, right, an initializer list. So the compiler knows the return type is vector of int. So it creates a vector of int initialized from that initializer list, returns that. On the client side, you can say for auto x colon foo, it knows that that's a vector of int, so now we're going to iterate across all the elements of that vector. Okay, so I'm completely not addressing performance issues here because we're going to address that a little bit later. But this is not, there's no big performance penalty here for returning the vector of int by value. You just don't know why yet. All right, so now gotchas. Unfortunately, there's a lot of them with this whole initialization stuff. So there's one gotcha involving overloading. Constructors that take an initializer list are preferred over ones that don't. So if the compiler can't tell, it assumes it's an initializer list. The vector container has an initializer that takes two values, right? The first one being a count, the second being a value. Notice this is just a parenthesis pair here. So this is the original vector constructor that takes a value and a count. So if you're trying to move toward C++11 style initialization, which involves using braces, and we're going to see a lot more of that soon, it breaks this code. Because when the compiler sees this, it says, oh, this is an initializer list with two values in it, so this initializes v2 as a vector with two ints. The first one's 10, the second's 20. Perfectly legal, just wrong. All right? And there's no solution to this problem other than going forward, don't design your interfaces such that it's possible to have this happen.
Legacy code.
It's an issue with legacy code, and if you're designing a class today, you would never give it this constructor along with one that takes an initializer list. You just wouldn't do it. That's the bottom line. There's no solution to this. So more about initialization. So this is another one of those slides that shows the potential issues, or the actual issues, in old C++. So here's a bunch of pointers being initialized in three different ways. Pointers to int. We can provide an initialized, dynamically allocated int, and initialize the pointer. We can leave it uninitialized, which is fine, and initialize the pointer. Or we can value initialize it, and the compiler will know that the value initialization, default value initialization of an int is 0, and this will end up being a pointer to an int equal to 0. All right? That's C++ 98 and C++ 11. What am I initializing v1 to here? 10. What about v2? It's a function declaration. Oh, yeah. So this is the simplest possible example of C++'s most vexing parse, which is actually a more complex example that Scott uses in his effective STL book. But this kind of thing happens all the time. You'll see what you think is a variable initialization, but it actually ends up being a function declaration for a function you don't even want, because the rules say that if something is ambiguous and it can be interpreted both as executable code or as a declaration, the compiler is obliged to interpret it as a declaration, not as an executable statement. An initialization is executable. So it'll pick a declaration over an initialization, if all else is equal, the syntax being ambiguous. What about this? What is that? All right? One possible interpretation is this is an int named foo that we're declaring and initializing to some value bar. But what's bar? Bar could be a type. Well, what does that make this? A function declaration. So not knowing what bar is means we don't know what this code is doing. We don't even know if it's a declaration or an initialization. Isn't that lovely? That's old C++. Initialize an int to 5.5. Sure, no problem. It just truncates. Initialize a double to some large number. Use it to initialize an int. No problem. Undefined behavior, but no problem. So these are all problems, really. All right. So in new C++, by the way, bar is a type. Now we know. In new C++, there is a new set of rules that if you start using braces to do your initialization instead of parens, all these new rules kick in that do a whole lot of sanity checking for you. It's not perfect, there's still gotchas, but it's a vast improvement. You just have to know the pitfalls. All right, so this does just what it did before. Initializes a dynamically allocated int to 10, and then PI1 points to it. Initialize this int to 10, no problem. This is still an uninitialized int, just like it was before. All right. Now, using braces for this one instead of parens, it is unambiguously an initialization. It cannot be a declaration. At least not a function declaration. I mean, it is an int declaration, okay. But it is an initialization of the int. That's what it is. No ambiguity. Now this, bar is the type. Now we know this is a function declaration. But if we expected this to be an integer initialization, right, and we get in the habit of using braces, the compiler will inform us we're not getting what we can't get what we want. So this becomes a compile error if you use the braces, because bar is a type. You can't initialize an int with a type. That's good. All right, here's our double with a really big value. We try to initialize an int to that using braces. It's an error. Narrowing is not allowed when you're using the braces. And not just ridiculous narrowing, even minor narrowing or truncation is not allowed. Any questions?
What would be the recommended way to get the narrowing if that is exactly what you want?
The question is, how would you get the narrowing if you wanted to use parens? Just go back to parens.
Or you can use static cast.
Yeah, you can always be explicit. It's a good idea to self-document, so use a cast operator for things like that.
With a cast inside.
If you have static cast inside the braces, then it wouldn't be narrowing by the braces, it would be narrowing by the static cast. Okay.
Right. So you can use parens with the static cast. You can use braces with the static cast inside it. As long as when the compiler is processing the initializer list, not the initializer, but the initialization, it doesn't see any narrowing or truncation, it'll be happy.
Will that, does the narrowing affect the sign? Like if you're expecting an unsigned card, and somebody passes it a -1, so the compiler,
Okay, the question is, what about cases where you have an unsigned, I'll transform that into the case that makes sense to me. If you have an unsigned int and you initialize it using braces from a signed, wouldn't compile. Okay. So here's the fine print. Narrowing and truncation of aggregates, arrays and structures, back to the first slide of this section, is always an error in C++11, even if it was legal in old C++. This is a breaking change. Notice it's in bold and underlined because existing code that works will stop working silently, or is it? No, it's not silently. It's actually going to give you an error. But it is a breaking change. Fortunately, it's not a debugging nightmare type of breaking change. So example, here's a struct with a couple of ints in it, and it's always legal to initialize it this way because this is old C++ syntax. And there's no truncation or narrowing involved. It's okay to omit the equal sign, but of course only in C++11. this is an error everywhere, but for different reasons. So it's an error in C++ 98 because you can't use braces to initialize. Wait a minute. Yeah, right. Thank you. Missing equal sign is the problem in old C++. And in new C++, it's a truncation violation. All right, so this one is an error in C++ 11 because of the truncation, but it's legal in C++ 98 because it's the old syntax for initialization, and old C++ lets you truncate narrow to your heart's content. This is an error in C++ 11, again because of truncation. It's okay in old C++.
I mean, that's a good thing.
Yes, collectively, this feature is a good thing. But if you work really hard, you can find a few places where the goodness becomes ambiguous. It's when you get into a really edge case, then it's confusing. So you have to just be careful, right? The price of freedom is eternal vigilance.
Bring out some more roads.
That's the way it is.
That case,
Another gotcha involves auto mixed in with initializer list. If you use auto, where it deduces the type, and you use an initializer list, the type that B gets is the type initializer list of something, something, something. Not really intuitive. Okay? And so to prove it, I'm using RTTI here, and I'm actually taking the value of A and the value of B and displaying what its type is. All right, so A has type, and it prints I, which is that compiler's way of saying integer, and B's name is blah, blah, initializer list, blah, blah. Okay? The salient portion is the initializer list in there. Be careful. Again, there is no universal solution to this. You just have to not mix auto and initializer list. Okay, so now we're moving to lambdas. So to set up for lambdas, a general issue in old C++ is algorithms are not efficient if you use pointers to functions to provide functionality. And that's because when there's pointers to functions involved, except in certain rare cases where the compiler has seen the implementation of the function before its use, it's not likely to be able to inline it. So if it's an inline function, it should be okay. If it's a non-inline function, okay, there's going to be a problem. If it's a pointer, it's probably going to be a problem, even if it's a pointer to an inline function. Right? What happens if you declare a function inline and then you have a pointer to it? It has to actually generate the function and then have the pointer point to that function when you use the pointer. But if you use the function directly, then it doesn't have to do that. But we're looking at the case where you do use a pointer to this somehow. All right, so here's an example. We're using an STL algorithm findIf. We're searching this range for the first value that is positive, the first one that satisfies this predicate. So calls to ispos are probably not inlined. The way I explained it doesn't really say why, because you'd think if it's inline, it was figured out. Probably because, generally speaking, okay. If we didn't have inline here, it's really clear it wouldn't be inline. I didn't make a pointer to it first. I probably should have done that to sort of underscore the fact that the compiler can't inline it. Compilers are getting really smart. Even if I did that, a really smart compiler might be able to inline it. The general case is anytime you have a function pointer being passed, and the name of a function is a function pointer, even if it's inline, it's probably not going to be inlined by the code generator. Okay, that's my understanding. I hope that's fairly close to reality. There's ways around it. There's these function adapters that you could use that eliminate the non-inlining problem, but they introduce hideous syntax that you have to deal with instead. So it's not a really great solution. Bind first, bind second, greater int. you can use these, you'll actually get better performance, but it's hard to maintain. So one typical solution, use function objects. Any class that has an implementation of operator open close means that any instance of that class can be used as if it were a function. So that's the definition of a function object in C++. So we'll do the same thing. We're searching through this container for the first positive value and pass it an anonymous instance of the isPos class. So isPos, notice the giveaway here, the capital I, it's a class, that's just a convention. The parenthesis here is not a function call. That's a real common misunderstanding when you first look at this kind of thing, to see parentheses and say, well, we're calling some function that takes no arguments. No, we're instantiating an isPos by putting the parentheses there. So we're passing an anonymous instance of an isPos. This the compiler can inline. Why? Because it knows the type of this. This is an inline function, therefore it can just take the meat here and throw it right into the code generation that it's doing on findIf, and there's no actual call involved. That's C++ 101 for the past 20 years. And that's where we were, up to C++ 11. Now, what's the drawback? Clearly, this is better than the previous slide where you're not necessarily getting inlining, right? There's a drawback to this as well, and that is that the code over here might be in a different translation unit from where it's being used, and if somebody doesn't know what this is, you have to go look it up to see what's actually going on. So there's a separation between the logic and the use of the logic. Question?
Another drawback to this is you can save some of the stack state. You have to save it up to the variable.
Okay. So the comment is if there's state that has to be saved, there's all sorts of additional performance hits for having to deal with the situation. Okay. So new C++ introduces lambda expressions. A lambda expression, which is source code, specifies an anonymous on-demand function object. Every lambda expression creates a class with a type name, the name of which you don't get to know, but it's unique. All right, so every lambda generates a uniquely named class, which has a function that is an overloaded function call operator that does what your lambda says to do. So I can take this functionality and put it right where I use it. And yes, it's generating a whole class and instantiating it and all that, but you know, it's inline and it's going to be very efficient.
Guaranteed the inline in that case?
Well, sure. It's like you're declaring a class like this with an inline function in it. Yeah, absolutely guaranteed to be inline. I mean, if it can be, right? There's rules about when inlining isn't inlined. Separate issue. You put a loop in here, it may not be inlined. If it's recursive, no, you can't do that. Well, you can, but you don't want to. It probably won't be inlined. Yeah. No, because of the simple fact that when you have a large function, it reaches a point of diminishing returns. Okay, aside, why is inlining good? What are you saving when you do an inline call? Call overhead, passing, returning arguments. If you have 1,000 lines of code in your function, what's the relative savings of the call and return part? Right, okay. Yes, yes. However, as soon as you declare it as inline, you have to be consistent in your syntax. So you still make it inline everywhere. The compiler just says, yeah, I'm not going to actually do it. But it has to follow the inlining rules, meaning every translation unit needs to see the definition. Okay. Okay, so there's a simple lambda. And we'll get in, okay, so part here that salient, the open close square brackets introduces a lambda syntax. And from that point on, it's like the function definition. So this is the parameter list, and this is the body. Notice there's no declaration of the return type. It figures it out. So it just looks at this expression. Oh, I wanted to show Herb's quote here. So at some point, Herb said, lambdas make the existing STL algorithms roughly 100 times more usable. And Herb never exaggerates. All right. So lambdas are all wonderful, but remember, a lambda leads to an instantiation of an instance of this class. which means that the names that are declared here aren't just automatically available in here anymore, because this is a function over here and the lambda is in a class defined somewhere else. So these names don't just automatically become visible inside the body of the lambda. Some names do, globals do. Okay? Because if something's declared up here, then it's visible to the lambda just like it's visible to main. And you can just use that name. And we'll get to that. We'll revisit that issue shortly. But the question is, how do you get access to these? And what's good style? All right, so if you put the names of variables you need in the square brackets, they're called a capture list. And you can think of it as these being data members of the class that the lambda is actually leading to the creation of. And the class instance is initialized with copies of target and epsilon when the lambda is instantiated. And then when you name target and epsilon in here, you're actually getting a local copy that was copied from out here. Which implies if you go in and change target and epsilon in here, you're not changing it out here. We'll get to more about that in a minute. But the default here is it's a copy by, it's initialization by copying. It's copying those values into the lambda. I saw a hand go up and go back down? Yeah. That's correct. If you, we'll see that you can actually create a lambda and save a handle to it and use it multiple times. If you change target and epsilon, these target and epsilon variables, you won't change the behavior of that lambda. It's been initialized at the time of its initialization. That's it. There's ways around this. We'll get to it. But that's kind of the simplest use of a lambda. Okay. So the capture list can be empty. If it's empty, it means you have no access to local variables at all. You try to use them, you get a compile error. Then each individual variable can be captured by value or it can be captured by reference. If you capture it by value, that's what we just saw. It makes a copy. If you capture it by reference, you're actually creating a reference inside the lambda class. And when you refer to it, you are referring to the variable that's out in the main's scope. Very dangerous, especially in a multi-threading environment. Okay? Because that lambda may go on existing while the function, obviously not main, right? This is main, it's going to be around for a while, but some other function, not main, can run, create a lambda, the lambda continues to do its thing, then this function finishes. And the lambda keeps running, and now it's got dangling references. That's a big problem. Well, it's not a problem if you don't do it. All right, so each individual variable can be qualified as captured by value, captured by reference. A personal gripe of mine is you can't say equals here, because you can say equals like this, and it means capture everything by value. You can say ampersand, which says capture everything by reference. You can have a mixture of references and values, but the values can't have an equal sign. Don't you think they should be able to have an equal sign?
Sure.
It kind of makes it all consistent, doesn't it? All right. And you can mix and match. You can say the default is to capture by value, but for variable 1, I want to capture that one by reference.
But clearly,
Okay?
that's scope
Only for the purpose of the code inside the lambda. You can, okay, the question is, what about the scope of where these things come from? The only things, the only things you can capture, regardless of how you capture them, are locals from the scope around the lambda. Not globals, not data members, only local block scope variables. We're going to get to that. In fact, we're getting to it right here. Only locals can be captured. I did not know that for a long time after I learned lambdas. I didn't really learn it until I was reading the review chapters of Scott's new book coming out, and he taught me this. So think of you being some of the first few people to see this written out and having it made very explicit. Capturing only applies to non-static local variables, including parameters to the function, because a function parameter is a local variable, just like the ones declared in the block. Within a member function, right, you can certainly have lambdas that work within the context of a member function. Data members cannot be captured. They're not locals. To refer to data members in that situation, you capture a local that gives you access to them. What's that called? THIS. If you capture this, either by value or by reference, you can then use that with the proper syntax to to access those data members. Another way that it might be simpler: take the data members, copy them into a local variable, then just capture the locals normally. All right.
We're talking about,
I have to here because I haven't even gotten to move semantics yet, and that's the most interesting part. So basically, avoid default capture modes, and when Scott's effective modern C++ comes out, that's item 33. Any questions? Avoid default capture modes. What he's basically saying is don't do this and don't do that. Always list out each thing you're capturing. It makes it really clear what you're capturing. And even then, it can be confusing when you try to use things like file scopes and file statics, because they don't really play in the capture game. Right? So it's still going to be a little bit confusing, but at least you can eliminate some confusion by never using default capture modes. Okay. So let's move on. Oh, in C++ and in C, it is illegal to have a local function within a function. Right? You cannot directly define a function in a function. You can define a class within a function and then put a function in that class, but is it worth that? Jumping through that hoop? Not really. But lambdas give you a way around this. So if I try to define a function inside of main, it's an error. But nothing keeps me from declaring an auto and initializing it with a lambda. The compiler knows what the type is, even if we don't. And the type is filled in, and now we have a way to refer to that lambda by name, and we can call it just as if it was an ordinary function. So essentially, lambdas give you local functions if you really want them. Yes? No. Once. It generates an entire class, but because that lambda is inline, there may not be actually any resources used at the time because of that. Everything is just inlined and optimized away. But conceptually, every lambda means an entirely new class has been declared. Yep. Okay. So C++ 14 adds a twist that simplifies code considerably. In C++ 11, if you have a situation like this, you have a vector of shared putters of string, and you wish to sort those strings, right? You can do it with a lambda, but you have to tell the compiler exactly what type both of the parameters are to that lambda. It's a const shared putter of string ref and a const shared putter of string ref, which is really kind of verbose. Then you can do the right thing to sort them. In C++ 14, you can just declare those lambda parameters const autoref, const autoref. And it figures out what the type is. What this really does is create a class template, or a class with a function template. And this becomes a templatized member function of that class. It just works. It certainly simplifies things. Here's another case where it simplifies things a lot. All right, go from this to this, taking advantage of this facility. So that's pretty much a win-win. Some other uses for lambdas. They're great for STL algorithms, like the predicates for if, comparators for the sorting functions or the associative containers like set multiset. With unique putter and shared putter, I know we haven't talked about it, those are the smart pointers of the library. You can give them custom deleters, special actions they perform rather than just applying delete when their resources have to be destroyed. The typical example is you can write a shared putter that uses file pointers as its data type. So to initialize it, you pass it the result of fopen. How do you destroy it? fclose, right? So you would provide fclose as the custom deleter for unique putter or shared pointer if the resource is a file star. That's a way to do it. Well, lambdas simplify that quite a bit. Easy predicates for condition variables when you're using the threading API. On-the-fly callbacks. You can install a bunch of callbacks using lambdas. It makes the syntax really easy. Instead of having to declare all your functions and then list them all in some separate place. Question?
Back when you were showing the example of finding handle for a lambda, can that be templatized?
Where? Oh, I missed it. Sorry. Oh, this was it. So question, the question, can you make this can you use generic lambdas for this? I've never thought about it. I don't know. How's that for a very, very precise answer?
That's actually instantiating,
Yes.
not just type it.
In this case, it's actually instantiated. Is it possible to somehow make this work with auto in here? My intuition says no, but what does my intuition count for? You know, there's so many.
Don't you have that just
Edge
the
cases.
example on the next slide? You've got auto, the last line?
I do, don't I? Auto get size equals. I guess so then. Never mind. Yes, you can.
But not in
But only in 14, yes. So because it's really a templatized implementation, what's going to happen is it's where you actually use this, where the client uses it, that's where it's going to actually do all the magic. Yeah, some of this stuff, it's kind of mind-blowing, what putting things together lets you do. Okay, let's go and move semantics here. We might end up a little over. In old C++, objects are or could be copied in cases where you really don't need them copied. And it's kind of a classic problem with the C++ language that value semantics implies there's a lot of stuff getting copied around. A lot of effort has been put into eliding the extra copies by having the compiler detect special cases like the return value optimization and make things work a lot faster. But that relies on compiler magic, and it's a quality of implementation issue, and there's no predictability. You can't declare something to use the RVO. You can only facilitate it, right, by writing your function in a certain way. So let's say we have a class big that holds a lot of stuff. It's expensive to copy. Right? So here's a function that returns a big by value. And then you use it. This may cost up to 3 constructors and 2 destructors in the worst case scenario of a really stupid compiler, because technically what the semantics here say is invoke this function, which creates an anonymous temporary, copy it for the return value, then destroy this. The temporary that's being returned is then copied into an initialization of BT, and then that temporary is destroyed. And then BT goes on living. 3 constructors and 2 destructors just to get past this call. In reality, it's probably not going to be that many because compilers are smart. But stupid compilers might, or in debug mode, that may actually be what happens. If you have a couple of bigs and you say big sum equals x plus y, and assuming we have an operator plus for bigs, even though this is passed by reference to const, which is the right way to do it, there's still potentially an extra big object being created and destroyed just because this creates a sum internally and then returns it by value. So it'll be created and destroyed. And then this return value will be created and then it'll be copied from and destroyed. Good compilers wouldn't probably do that. But again, it requires smart compilers. The functions could be rewritten. So instead of returning by value, They return by reference. Really bad idea. Because then who manages the memory? Returning by reference when there's some sort of object that has been created as a temporary of some kind is, a disaster waiting to happen. Okay, return a raw pointer. Raw pointers in general are being retired from C++. You can use a smart pointer. Okay, so a little more syntax for shared putter, more overhead. That's probably the best, definitely the best of those three solutions. Okay, but if we know something, or the compiler knows something about that returned object, specifically that is indeed a temporary, after we use it, it's going to just go away. That knowledge allows a different implementation. So we're going to learn how that works. But first, terminology. So everybody's heard the terms L value and R value. And how many of you just think of it as what's on the left or the right of an equal sign? Not too many anymore. Okay. Here's what they mean in C++ today. This is what counts. Forget about left and right side of an equal sign. An L value is a thing you can take the address of. It may or may not actually have a name. For example, star putter doesn't have a name, right? Putter does, but star putter doesn't have a name. But you can take its address. It's an L value. An R value is something you can't take the address of. Usually it has no name. Literal constants, temporaries of various kinds. So that's what L value and R value mean, roughly. Close enough for this discussion. So here's a piece of code that shows both L value references and a new type called an R value reference, which is declared just like a regular reference with an extra ampersand. So I is an int, RI is a regular old L value reference, RRI is an R value reference. The rule is an R value reference binds only to unnamed temporary objects, aka R values. That's why it's called an R value reference. So this is fine. 10 is an R value, right? It doesn't have a name. This is an error. I is an L value. You can't point to it, refer to it with an R value reference. It's a compiler error. You take I and add 10, the result is a temporary. Perfectly fine to refer to that result with an R value reference. Certainly the result of this doesn't have a name, it just has a value. And a type, but it doesn't have a name.
So can I say I plus 0
Sure. Oh,
in the third line?
here? Yes. Wait a minute, can you? I plus 0. Yes, that would be perfectly fine. Yep. Okay. Fn, error. This is an L value reference, and you can't use it to bind to a temporary, which is what Fn returns. Fn returns an int. You can't refer to that with an L value reference. I can refer to it with an L value reference to const, however. That's an old C++ special case. Right, what the compiler does in this case is it actually makes a copy of that int, stores it somewhere, makes this reference point to it, and it guarantees the lifetime of that temporary is at least as long as the lifetime of the reference. Everything works fine. And finally, an R value reference can be bound to a temporary returned from a function. Okay, any questions on this? No? Good. Okay. Copy versus move operations. So C++ has always had the copy operations, the copy constructor, the copy assignment operator. That's ancient history. New C++ adds move operations, the move constructor, the move assignment operator. The purpose of these functions is if the move or the copy can be implemented, the move or the assignment can be implemented by stealing the guts of the source and just reinstalling it into the destination, it will do that. So if you have something that's very resource intensive, it typically is implemented with some kind of pointer. Smart, stupid, whatever, a pointer. One of these applied to that type will usually just involve copying some pointers across. The actual data could be megabytes and megabytes, but it's represented with a couple of pointers, and these operations will perform the move that way, very efficiently. They will leave the original object, the one being moved or copied, moved from, move constructor, move assigned, they will leave it in a state where there's very little you would want to do with it, but it's legal for them to be destroyed or reassigned to. Typically, that's all you would ever do with them. And usually it's not even reassigned to. Usually they just get destroyed. So, well, they had names in some other context, okay, but not in the context of this function. And in fact, yeah, they wouldn't really, there wouldn't be any way to have a handle to these objects. And if there is, that's a problem.
So how do you modify the objects that you're moving?
Okay, hold on. We're going to see a lot of code here. This is just the beginning. Oh, and just an aside, both of these would typically be declared no except, but that's a performance issue. We're going to just ignore it. Okay, so here's a fleshing out of the big class with these move operations. So big has got a constructor, destructor. A constructor takes an int. Copy operations, move operations. Now, to make this a little more real world, instead of having all the big data be directly declared here, I'm going to actually say there's another data type called blob, and that really has all the big data in it. And we're going to just contain a blob as a member, and then we'll add like a non-obese object, for lack of a better term. I can say that now, I'm losing weight. Anyway, so the combination together represents a heavyweight object, right? It takes a lot of resources. But it's broken up into two pieces, so we can see how to deal with the two pieces independently, because that's really the interesting part. You know, what do you do to deal with this versus deal with that? And how do you implement these functions? Okay. So let's say we have the ability to add bigs. You take two bigs and add them, and you get a big. You can munge a big, which actually does not modify the original, but returns a modified copy. And you have like a big factory that returns a big. So how many actual full-scale objects are being created? What I mean here is how many times does the compiler have to completely populate a full big with all of its data? When does it actually have to generate all that humongous amount of data? It turns out, with move semantics in place here, this might require will probably require only a single big to ever be created. So where is that big created? If you go into make big, right here, it's created. But then it's returned as an anonymous return value. So that means it can be move assigned into A. So that move assignment, I don't count it here, because that's a cheap operation. If I say big bx plus y, again, the only time it's really fully creating a big is right in the operator plus, where it actually does the work. And then when it returns, it's returning by value, but that value is a temporary. Therefore, it's going to use the move constructor here, and it's going to steal the contents out of that temporary, and B will end up being the owner of those resources. But it's not fully replicating it. It's not doing a deep copy. It's doing a shallow copy. A equals x plus y. The only difference here is this is going to be assignment rather than construction. It's still one object. Okay, for something like munge, there's still going to have to be two created. Why? Munge itself takes a reference, but it returns a different object. So that's one, right? And then plus also creates an object. So the addition creates one, and then munge is going to create one. So there's two that have to be created. There's no way around it. Right? That's just the way it is. If we do a swap, no temporaries are created in the generation of that code, if everything is correctly implemented. So a return value's contents can be moved to a destination object as long as the type that triggers the function that's doing the move has been enabled for move semantics by providing those move functions. All right, so now we're going to drill down a little bit. But before we do that, I want to share with you a little bit of history about my understanding of move semantics. So the first time I was ever exposed to this, Scott Myers taught his overview of C++11 about 5 years ago. And that was really my first ever exposure to move semantics. And it was all kind of mystical, and I sort of got the benefit of it, but 2 days after I came back from that course, I couldn't sit down and write a class that used that. So then some time went by. I attended a talk that Dan Sachs gave with his son in Boston. And the Sun actually gave a talk in Dan Kibitz. And the talk was on move semantics. And at the end of that hour, I go, wow, yeah, now I get it. Now it really makes sense. And a week later, it's like, now wait a minute, how did that work? And I could sort of know why it's good, but I couldn't reproduce it. Eventually, I saw something that made it all click. I'm not saying it should make it click for you. This is just what did it for me. It was swap, standard swap. So this is an implementation of standard swap from the old C++ library. If you're just going to swap two objects and you don't know anything about them, right? A function template has to create a temporary copy of one, copy the other parameter into the old initial value, and then copy the temporary back into here. It'll always work, but there's 3 copy operations involved. 1 copy constructor, 2 copy assignment operators. These are all deep copies. That's very expensive, but it's universal. Pardon?
Potentially.
It's potentially expensive if those objects are large. It's going to do a deep copy in old C++. That's just the way it is. There's no alternative. You could always write a custom swap for that type that does it differently. But if you use the standard swap, that's what it's going to do, a deep copy. That's it. If you provide a big class and you give it move support, you give it the move semantics so that the previous example is nice and efficient, this is still going to be inefficient. Just move enabling a class is not sufficient to make something like this take advantage of it, because there's no R. Everything's an L value. There's no R values. Everything has a name. The objects here can be referred to by pointers and references all over the place outside this function. There's no assumptions that can be made here to optimize this into move operations. This is the implementation of standard swap, more or less, in C++ 11 and going forward. So you'll notice this part's the same. If we compare the header line, both the template declaration and the function declaration, they're identical. The difference is that in here, we use this funky move operator, whatever that is. So think of move as a cast to R value. That's really what it is. Technically, it's just taking X and it's making it behave like an R value. Well, if the result of this is an R value and we construct temp from an R value, that will allow the compiler to employ the move constructor. If we move Y and assign to X, it can use the move assignment operator. And again, over here, it can use the move assignment operator. So what it's doing is just doing a shallow copy for all 3 of those operations when those operations are available. And if you use this on a class that has no move operations, the result of casting it to an R value, even if it casts it to an R value, it'll still end up binding to the copy operations, because that's all there are. And the compiler allows that. So it'll still be just as inefficient if you don't move enable a class. But if you do, then this version of swap can leverage that. So this really meant, this sort of was the key to me to understand why this is, how this all works together. So now let's finish up the big. So here's an implementation of the move constructor and move assignment operator for big. Remember, blob really has all the data in it, right? So the move constructor will move the blob, and it doesn't care about X. There's no reason to do a move on X because X is just a double. Can you improve the move of a double over what you would do if it was being copied? No. So that's, you just don't worry about that one. But here's where the potential benefit is. For the assignment operator, we do a move on the B part. We do a regular copy of the X part. Return star this. That's correct. But now we have to look at blob. How does blob fit into all this? So here's the implementations of the move operations for blob. The move constructor is going to steal the pointer from the right-hand side object and install it in the object being constructed. Then it's going to take the raw pointer from the right-hand side and null it out. That's perfectly safe. At some point later on, it'll try to delete it. deleting a null pointer is legal.
But
In this case, RHS is saying R value, and you're saying take the R value, which has no reference.
Okay, stop right there. The comment is, in this case, RHS is an R value. Actually, it isn't. RHS is an L value that has a type R value reference. You like that? RHS is an L value. It has a name. It has a type that is R value reference. Don't shoot the messenger. Let's look at the assignment operator. RHS has type R value reference. If it's not a self-assignment, it's questionable whether you need the check for self-assignment anymore, but this is an old-fashioned delete and copy, so we need it. So if we do it this way, yes, we have to test for self-assignment. We want to release the old resource because we are, after all, assigning to an object. But from this point on, it's just like a copy, a move construction, right? So we steal the pointer and null out the original. Do you see why these are not const? Right? It's not const R value reference to blob. It's non-const R value reference to blob because we're actually modifying RHS. So we can't declare it const.
So in the second case, the move assignment, what's going to happen to the actual blob?
The actual blob. Which actual blob?
Okay, so the blob on the right-hand side.
Okay, so this right-hand side's data is being transferred into the implicit object being assigned to. That's what this assignment does. The pointer to all the data is now owned by the new object, and the original pointer has been nulled out. All right, so that's really the heart of move semantics. Yes? Right. It's an assignment of pointers. It has to happen.
Right, but why this metric of the, that's doing that pointer, nothing to do with.
All right. I'm sorry. I don't quite understand the question. It's probably going to take all our remaining time for me to understand it, so let me just try to finish up. I'm sorry. Come see me after, and we'll try to figure it out, okay? Let's move on. We don't have too much left. When does double ampersand actually not mean R value? Scott Myers came up with the term universal references. There are certain contexts where you use the double ampersand to modify a parameter. If that happens in a type deduction context, which is typically in a template declaration, the meaning of and becomes different. It doesn't mean R value reference. It means something that could be either an R value or an L value reference depending on the situation. So here is a deduction context. Remember I said that auto uses template deduction rules, template type deduction rules? If I say auto ref x equals something, it's going to apply template type deduction to this. What type is x? X is actually an R value because this is an R value. So that's the type that gets. On the other hand, if I have a regular variable pi and I say auto ref y equals pi, now the type of y is an L value. I can't just make it an R value reference because this has a name and something else can modify it. Therefore, the compiler sees that and this becomes an L value reference. Okay. In a template context, we have a function template that takes a reference to T. And the only time this happens is when it's exactly parameter ref. So no extra decoration, no const, no stars, no nothing. Template parameter, type name, ref. That becomes a universal reference. What does that mean? If I say f of 3.14, the function that is instantiated has this signature. F of double, it takes an R value reference. Why? 3.14 is an R value. If I say f of x, x is an L value. This is the function. Whoops, what happened there? What's x actually? No. X is an R value. So f of x generates this. F of pi is an L value. That generates a function with this signature. So even though it's declared one way, it ends up sort of landing as either an L value or an R value. Again, it's a Schrodinger's cat scenario. If you're not familiar with that, it won't make any sense. If you are, it's kind of a perfect fit. All right, so what's behind that? When Scott came up with the term universal reference, it was as a simplification. There's some great videos of him giving this talk about about move semantics, and what he says right at the beginning is, I'm going to lie to you, but it's a useful lie. Have anybody seen that video? A couple. So what Scott is trying to do is not tell you this, because it'll make your brain explode. Okay? References to references in a universal reference context, when there's type deduction involved, have the property that if you have a pair of references of the same or different type, there's rules of what that actually translates into. So an L value ref to an L value ref is an L value ref. An R value ref to an L value ref is an L value ref. An L value ref to an R value ref is an L value ref. The only thing that ends up with an R value ref is an R value ref to an R value ref. Stéphane Levavé, who I don't think is here yet, has said L value references are infectious. If there's an L value reference anywhere, it rules. And if there's no L value references, then the R value references become the type. So example. Here's a function template f that takes a universal reference. And here's the double pi. If I say f of 3.14, that is processed by the compiler when this thing is plugged in as f of R value ref to R value ref, right? Because this is a double ampersand, and this is an R value. Therefore, that becomes this. If it's f of pi, it's an L value ref, which is pi, to an R value ref up here. Or it's an R value ref to an L value. One of those two. Anyway, it ends up as an L value. And that's what counts. So reference collapsing is the actual mechanism in the standard that explains the simplification Scott calls universal references, which he characterizes, I think, quite wisely as a useful lie. It's a little bit simpler. But some people say it's not. This is actually simpler. I'm agnostic. I think they're both valid viewpoints. Okay, I know we're over time now, so if anybody needs to leave, feel free. But we haven't talked about perfect forwarding yet, which is really cool. So I'm going to do that. Okay, how many constructors would it actually take if you have a bunch of expensive subobjects? In the example we just said, there was one blob in there, right? It was simple. What if we have 3 or 4 different data members that are like blobs? If something is a blob, it's going to be treated like an R value. If something's like a double, you want to treat it like an L value. But the more of these you have, the more combinations of constructors you might need. And it's an exponential explosion. So if you have 2 different objects, one of which is a blob, one of which is a large and one, well, actually in this case, they're both large objects. Okay? When someone creates a block, they might pass 2 L values, they might pass 2 R values, they might pass an R value in an L or an L value in an R. Each of those has an optimum implementation. And we need 4 variants. We need the one that takes an L and an L, an R and an R, an L and an R, and an R and an L. And then we put the moves in the appropriate place. This is sort of doable when there's 2. What about 3 or 4? You see the problem? Okay. So then it becomes untenable. The solution is you make the constructor a function template. The class itself isn't even necessarily a template, although it can be. The function is a function template using universal references. Instead of doing the move, you take each of these and you standard forward those parameters. Remember how I said move is like a cast to R value? Well, a standard forward is like a conditional cast to R value. It'll cast to an R value if it's an R value. It won't if it's an L value. So it'll basically pass the object in its true nature to whatever function we're passing it to, the blob constructor and the string constructor. If it gets passed as an R value, it uses the move constructor. If it gets passed as an L value, it'll end up using the copy constructor. And it just works. Yeah? Yeah, I'm not a matrix person. I don't work with them, so I know there's certain implications of matrices, but I'm not really sure how to translate it to this. All right, so the point here is no matter how many parameters you have, this is just linear. If you have 3 of them, you have 3 lines. 4 of them, you have 4 lines. And then at compile time, it'll actually look at the specific use each time because this is a template, and it'll generate another instantiation if it needs to, and it hasn't before, that's perfectly optimized for that permutation of L values and R values. And that's perfect forwarding.
So that basically works because string and blob have move constructors.
The question is, does that work because these both are move enabled? Yes. But even if they weren't, it would still work. It just wouldn't be as efficient.
Right. I mean, it works in the sense of exploiting the R value.
Absolutely. That's the point. The way this is written is it exploits any move semantics these things might have. I mean, when we write this, we might not even know if string has move operations. In fact, it does. But if we didn't know that, this is still the right way to write it, and it would still be optimized. So it's the best case scenario. When move enable a type, we've seen that if it has a lot of data, it makes sense to move enable it. If you can't improve on what it do, if you can't improve on what it already does to copy, don't bother creating move operations. It's just unnecessary complexity. It just generates code for no apparent reason. Most library components are move enabled. Some are move only. Unique putter, not covered later for you guys. Unique putter is a move only type. So you can move it, but you cannot copy it. Why can't you copy it? Because it's a unique putter. Okay? Internal implementations of many components employ moves whenever possible. The classic poster child is vector. When a vector reallocates, and it has to actually transfer all the data from where it was to the new area in memory, now it's going to move. It used to copy. Yay. All right, so we used to have a rule of 3, right? Anybody remember the rule of 3? Basically, if you have to write either a copy constructor, a copy assignment, or a destructor, you should probably look at the other 2. You may not necessarily have to write them, but you should think about it. Now there's a rule of 5. If you declare any of the copy operations, both of them, or the move operations, both of them, or the destructor, one of them, no matter how you declare, even if just using equals delete or equals default, then you should probably declare all 5. Notice I'm saying declare, not necessarily implement. All right, you might, if it's equals delete, obviously you're not going to be implementing them. But you should declare all 5. If you declare any of the 5, no move operations will be generated. However, the copy operations are still generated because that's legacy behavior from C++ 98. That behavior is deprecated. So in the future, maybe in C++ 17, the compiler will no longer generate copy operations for you if you provide any of the 5 yourself. That'll be a breaking change. But it's a good thing. All right. We're pretty much out of time. And I'll do this one because it's C++ 14. In addition to all the capture modes we've already seen, in C++ 14 there's also this funky syntax where you can specify a local variable in the lambda being initialized from a variable local to the scope around it, and that allows you to use the move operation. In C++ 11, there's no way to move initialize the things you capture. In C++ 14, there is. That's really all I want to say about that. This is the sort of thing you just remember in the back of your mind, it's there. And when you need it, you can look it up. Last words. Is C++ too complicated? Be honest, how many of you have thought that? I've certainly thought that. So how do you measure complexity? Is it number of pages of language specification? It kind of depends on the font size, doesn't it? But okay, so the C++ 98 language, just language, not library, 300 pages. C++ 11, 424 pages. Compared to what? Java, 606 pages. C#, the last one I could find, 531 pages. It kind of looks like C++ is actually a simpler language. Maybe that's not the best way to judge complexity, or maybe it is, I don't know. I'd like to suggest some different metrics. To what extent does good code rely on undocumented idioms? Remember all the gotchas, all the ways you get in trouble with old C++? How many of these gotchas don't show up till you're debugging? Can you just say it in code, or do you have to explain it all in comments? How hard do you have to jump through hoops to get better performance? I think if you use any of these metrics, new C++ looks pretty darn good. That's my conclusion. All right, so some resources on my website. I've got a page of links. And in the PDF, all the rest of these slides are in there. Feel free to peruse. I'm going to skip just to one final word. Oh, hi, Ray. Even though I had to update you last night, I forgot. Anyway, there are only two kinds of languages, the ones people complain about and the ones nobody uses. Bjarne Stroustrup. Thank you.